Oh, good evening, guys. Sorry about my dishevelled appearance, but it was a bit of a rush to get here. My name's Blake Rain. I'm from Inchora. I just thought I'd do a talk about, just a quick one about some of the uses of Haskell at Inchora. We have some fairly large projects that we use functional programming for. I thought I'd talk particularly about just some of the stuff that we've been doing with it, rather than going into any details of any of the actual technical implementations. So to give you a quick overview, the Inchora group comprises of a number of companies that were brought together under a common vision, and this required the centralisation of a lot of the technologies that came with them. We're going to focus primarily on Inchora Home technology today, just to kind of keep everything nice and brief. So at Inchora Home, we have a system called Sulu, which provides a tenant notification service. So that's when people move in and out of properties, they're able to we notify all the councils and the water companies and the electricity companies that people are moving in and out of properties. So that makes sure that all the billing and everything is closed properly and you don't get a bill for people who haven't been there and all this sort of thing. This is a service that goes out to a few thousand letting agents, and they enter the information on here, and part of the service that we offer is a concierge service for the tenants that are moving into the property. And what that entails is we sort out their media for them, so that's setting up broadband and TV and anything like that. We sort out energy switching as well, and then any insurance requirements they have. So off the back of a website, we have a call centre. In fact, we have two call centres, and end to end, the whole thing is controlled by a set of Haskell programs. So the main site itself is built using Yesod. We use the persistent and the Esquelito libraries in order to do our data bindings. And we have a number of integrations with agency software. Again, we're using Yesod for all the APIs in Haskell. And they allow us to build the stable APIs. We also use that for our evolving APIs, which is when somebody just comes on board who has specific API requirements. We're able to rapidly develop them. An API there. We also use scripting for JavaScript because we have a number of things that happen throughout the ecosystem of the business, which is where we need to be able to very quickly change the way that the system behaves, which we can't really do with, Haskell's very good at this sort of thing, but we can't really do it by deploying lots of things. So we have a scripting system built on top of the Haskell infrastructure. Then behind the scenes, we have the call center management. So that's the campaign management, which is how we take a look at when we get new information presented to the system, new people that have come into properties or people leaving properties. How do we work out what we can sell them? How do we work out when we can call them, and so on and so forth? We're not based in London. We're based all over the place, actually. Our head office is in Farnborough, and we've got offices in Grantham, Norwich, and Glasgow. Then we have the adaptive dialer, which is when you've got multiple call centres with multiple products, you need to be able to say to people, okay, this is the next person you need to call, and you need to be able to do that as rapidly and as intelligently as you can. So in order to support this, we have a dialer system, again built in Haskell, which interfaces with the Avaya phone system, which allows us to control the call centres. And we have two call centres, which are the Grantham and the Glasgow offices. So there's a kind of quick summary. Obviously, there's quite a lot of stuff there. So I'm only covering, we'll take a look at some of the scripting, because it's quite interesting. One of the nice things about Haskell is that we can automatically generate all our bindings for all our JavaScript on our server side, and we don't have to, and we can rely a lot on the type safety. I'll also take a look at some of the campaign management, because that's one of the interesting things that Haskell lets us quite trivially build. So, using Haskell and JavaScript, we have numerous APIs because we've got all these letting agents. Some of them are very large letting agents and very complicated and have big operations. Some of them are quite small. And so we need to be able to build APIs. So what we often do is we have the stable APIs, which are written in Haskell, and then we use scripting on top of the Haskell system using JavaScript, which allows us to build simple APIs. And this allows us to make sure that our JavaScript scripts, which are quite throwaway and quite easy to make, they are essentially combining Haskell functions behind the scenes. So that allows us to build quite complicated things without having to go to Node.js and run the risk of having inconsistencies between, for instance, the persistent system that we use in the Haskell code in order to generate our data bindings, and then the equivalent in the Node.js. We're able to just do it all as all part of one system, which works out quite nicely. We have campaigns and queue management, all sorts of things like commission schemes and so forth, and all of these change quite a lot. They change really rapidly. We can have a new product where we, from inception to going live, is in a matter of days. It can be very, very quick. And of course, the contact center strategies, which is essentially taking a look at maximizing the conversion of a contact center. So you need to think about, when we're calling somebody, how often we've called them, and all this sort of thing. These strategies can change quite quickly. And if we wanted to deploy a Haskell program, and these are quite big programs, if we wanted to change them and deploy them for every single time, we would just be continuously changing server code and constantly trying to deploy things, and we would always have this huge backlog. So the other problem is that we ended up finding that we had a higher barrier for entry, which was that Haskell code, when you're dealing with things that are quite simple, is very easy to understand because it's a very natural way of expressing a function to use functional programming. And we're all functional programmers, I'm assuming, and so we know that that's the case. It's very easy to express stuff. But for when you get into non-trivial programs and quite large programs, that barrier for entry does go up. It can take people a lot longer to understand any complex system, regardless of the language it's written in. Whereas using JavaScript, anybody can use JavaScript. It's very simple. It's a very simple language. So it allowed us to let people who weren't Haskell developers develop custom functionality for the platform. So that, in essence, is sort of why we started using JavaScript with Haskell. And one of the nice things about Haskell is that we have this type system. We have all this type information about everything that is available. So we're able to automatically generate bindings into JavaScript. In essence, every single entity that we have in our data model, barring some particulars, we're able to automatically generate all the if you want to say JavaScript classes for every single one of them, all the prototype functions. And because they're essentially just hooking into JavaScript code, then through an FFI, through a foreign function interface, we're ensured that they're only calling Haskell functions. So any of the I/O that the scripts essentially perform is actually just calling Haskell functions. And the system we use to marshal data between JavaScript and the Haskell side is the ASON library, which is a lovely library for transforming JSON, and that makes sure that all the data that we're transferring between the two is nice and reasonably reliable. The particular JavaScript library we use is one that not many people have heard about. It's called duct tape. The lovely thing about duct tape is it's a very lightweight JavaScript engine. So have many of you heard of SQLite? Yeah. So SQLite compared to like Postgres, yeah. Duct tape is like that to V8. So it's very, very lightweight. And one of the nice things is that plays wonderfully into Haskell's lightweight threading. And because Haskell, being functional, has a very lightweight green thread system, and duct tape, each time we create a heap allocation, it's a couple of kilobytes. One of the things we can do is we can say, well, we can just create these new contexts without worrying about running out of memory or resource usage. And so we're essentially able to spin up a Haskell thread, which is very lightweight, create a whole new context for that thread, and then have this great big pool of Haskell threads and contexts that receive messages, run sorts of scripts, and if they fall over, it doesn't really matter. And so that plays quite nicely. And so duct tape was quite a good choice for that. However, as things progress, as they naturally do, things get more and more complicated. When you create a scripting system, I should have known this, it gets abused and then it ends up being used for absolutely everything. So shot myself in the foot, so now I've got to look at Chakra Core, which is, for those of you who don't know, the Microsoft Edge browser. It's their new JavaScript engine. And it's very nice. It offers a very nice API. The other option, of course, is V8, but I didn't really want to go there. So anyway, back to Haskell. So there's example uses there. We won't worry about that too much. But essentially, the automatic generation of the binding allows us to take a Haskell function just like this one. So this is a function that takes the ID of a letting agent and the ID of a product category. It runs in our SQL monad. We're able to automatically generate bindings against that, and we can generate the bindings in two ways, or both, depending on what we want. We can either generate it as an instance function, in which case we're able to call it on every instance of every object, or we're able to have it as a static, in which case all of the arguments are immediately marshaled. So essentially what we have is a great big file that has a load of template Haskell in it, which generates all these things, like the instance methods for common things like loading and saving from the database. And then we have, every time we have our set of controllers, like this sort of thing, we have exports of those. And again, it's a template Haskell function, which generates all the marshalling and everything that we need. And it quite simply looks at things like, if this is a function over letting agents, well, we know it's a function over letting agents because it takes a letting agent as an argument. And so it will automatically create instance methods and things like that. So the next thing I wanted to talk about was campaign management, which is one of the interesting things we ended up having to introduce into the system. There's no more JavaScript now, you'll be glad to know. Because in Inchora Home we have multiple product journeys for all the customers. You know, primarily this would be media, energy and insurance. But if you imagine, there's actually quite a lot of concurrent things going on within that. For instance, if we sell you an energy product, well, a year later, they may have a new set of tariffs open. So we then need to sell you, and we need to talk to you again because chances are you can be on a better tariff. And the same with things like insurance as well. And then you've got things like, what about if we ring you and we need to ring you again a couple of hours later, or maybe the next day, or all the appointment management. So there's an awful lot that goes into a call center, and we need to be a little bit intelligent about how we do this sort of thing. So the campaign system was built to allow us to be a little bit more flexible, rather than just getting a piece of data in, putting it in a call flow and that's about it. We needed to be a bit more selective about some of the stuff that we did with them. And we also needed to be able to do this at various points within the lifetime. So, for instance, when we first get the data, when somebody has actually been contacted, when somebody has been contacted and that has resulted in a particular outcome, all those sort of things. So, for instance, if we ring you and we leave a message and then you don't answer maybe 5 times, well, it doesn't make sense for us to keep ringing you, and it's also illegal. So what we do is we send you a text message to say, we're trying to ring you, because you wouldn't know otherwise. And all of this needs to be triggered, and there needs to be a number of decisions made about how we do this sort of stuff. It also needs to be accessible to contact center management, because unlike the scripting system, which changes quite slowly and is only ever used in sort of extreme circumstances, apart from when they use it for everything, the campaign system needs to change very, very rapidly. And quite a lot of these campaigns, the managers need to be able to take a look at the sort of strategy that they're applying. Refinement by scripting. We'll just ignore that for now, though. So to give you an idea of what a campaign looks like, this is a really, really simple campaign. They're built using a diagram system, which is in the management web interface. The managers can go in there, and they can drop these nodes, which you guys look at, and you immediately know what's going on here. Essentially, we're looking at, has the person had an insurance call, and was the offset from when they're added less than or equal to 7? That's 7 down there, not 0. So essentially what we're saying is, were they added less than 7 days or less, and have they had an insurance call? So that little campaign they can put together, and they can either leave that and have it, for instance, filling up a dial queue, and then associate people with that dial queue, and so people will start calling the data that comes through that, or they could plug it into a text message system, or they could export it because they want to do something else with it. The campaigns themselves do get very, very complicated. I tried to actually fit one of them in the slides, but it didn't fit, unfortunately I didn't understand it either. So there we go. But the campaign system is really quite, I don't want to say elegant because that sounds very, very arrogant, but it is quite good fun. So essentially what it is they create these diagrams, which we know is just an AST, so, but they don't know it, they don't need to know that. So they create these diagrams and connect them together. And we essentially get the data structure on the left here. I've grossly simplified for the sake of convenience. But what we need to do is we want to type that because we want to make sure that everything's sane, so that people aren't doing things like, well, you know, was the added date less than how many calls, whether they've had a call or not, and all this sort of thing, because we want to make sure that things are rational. So one of the nice things we can do with Haskell is to take that structure on the left and turn it into what's called a GADT. That's a generic algebraic data type. So you've got a normal algebraic data type on the left there, and here you have a generalized algebraic data type. Yeah. And the nice thing about a GADT is that we can capture type variables within the actual individual constructors. And those of you that know Haskell will see the error that I've made here, which, and those that you don't, these A's should have been T. So if you can just pretend that that's what I've done, that'll be less embarrassing for me. So essentially we can build these structures up, and we can build them with a very simple function that takes these simple expressions on the left-hand side, and the result of it is either a type error or it's going to be type T over A, not bool. And so in essence we're able to take each and every one of the constructors here and map it over to a typed variant. Does that make sense? Marvelous. Then we need to generate the actual SQL, and each of these diagrams essentially just turns into SQL because we need to be able to run it against the database. Running it against the database is quite easy. We take our typed expression as the first argument of our compile function, and we turn it into an SQL expression. Now, the Esquelito system has this wonderful way of having values wrapped inside expressions, which complicates the type a little bit. But essentially, we just have a reader monad here, which allows us to pass some environment around for the compiler. And we take our typed expression, and if we were to have, for instance, the lead added node, where we're saying, you know, when was it added, all we do is get our environment and inspect the lead added field, you know, using essentially lens-like format. So this allows us to build up the SQL expressions, and I gave a quick example here. If we wanted to be able to go from a Boolean expression to a list of entities, we could say select from, this is Esquelito syntax, and just use our compile function here. So we use this all throughout the system to allow the management to be able to go in and say, actually, I want something more than just, you know, simple drop downs. I want quite complicated diagrams, because they have all sorts of interesting rules going on. And so that allows us to very quickly do this, and to make sure that even if they put together a diagram wrong, we're not going to try and run it against the database, and they're not going to get nasty 500 errors. The user interface itself does have, that allows them to build those diagrams, does actually have a little bit of a, if you like, a type checker. Calling it a type checker is really, really too generous, I suppose, but it does have a little version that just gives them a little bit of visual feedback when things go wrong. Fantastic. Did I keep it just under 30 minutes? Thank you very much.